But now we have a discussion period. And so this is pretty much free form here. If you have something you want to talk about, some of the people who've attended but not spoken maybe have some ideas they want to toss out or discuss. Now's the time to do it.
Sandy has her hand up.
Go ahead.
I was just gonna say, I don't think his slides are available on the website. So, and because we can't ask questions, it might be helpful. Can he submit those to us?
We certainly hope to get them.
Okay, yeah, if you can and add those, then we can re-review them because we can't even. He said that his email was on the first slide and then said it. And there's no way I'd be sure to have the correct one. So I'm not sure if you all did either.
I can give it to you.
Oh, I don't have a question. I just mean if somebody else wanted to
okay.
ask a question, you know, there's nothing to look at. So it would be good to have those slides.
The question I have is, did Rod make a version that doesn't have the recording? Because the version with the recording is 700 meg. So we'll have to ask.
That would be a good case for what Sandy was just asking for, and having just the slide deck sent over.
Right.
Yeah, we'll see what we can get from him. At the very least, hopefully he submits something for the proceedings. So he'll be able to read some of what he said, but before then, maybe we can get some static slides that take up less space.
Sandy, you can put your hand down now.
I noticed the number of comments about where's the noise of the kitchen coming from. It was not my kitchen.
No, it was Rod's cafe or his kitchen, or I don't know where he did that from.
Oh, that's funny. I thought for sure, Larry, that you walked away and didn't realize that you were making the
He was
banging
having a
and
good
clanging.
meal, yeah.
Oh,
No.
no.
That's funny. I tried muting you, but that muted him too because I forgot that it went through your computer. So that was funny.
So do you have any questions for the speakers who are still online? I think most of us are still here.
Like Blaze has a question.
Yeah, so I have a question to the community here. In my talk, I mentioned capstan drive instead of pinch drive, and this just seems to be something I do a lot when there's so many problems that I feel get better with a capstan drive. But at the same time, I keep seeing that in the climber competition community, no one's doing them. And I've had comments from, I think, Martin, that they used to try them once upon a time. There was a lot of problem with slippage, but without much detail on what exactly the problems were. And so I'm hoping, we've got a big group of people here who've done a lot of stuff in space elevators. Maybe some of them know more about why you wouldn't want to do a capstan drive.
I'm not the right person to ask this question, but if somebody can get this article to you, it was written by Keith Lofstrom called Acoustic Wave Powered Climbers. He shows an interesting design where the tether goes through a maze of rollers, instead of being pinched. I guess to gain friction. It's pretty cool, but I only have it in paper form, so I'd have no way to share it with you.
I'm very familiar with that paper because I presented.
You are okay, so you have seen that.
Yeah.
I think that question from Blaze goes more to Shuichi or Morty, because it's a competition thing where practical climbers play a role, and a lot of that experience should show up from there. So if they are still on here, Morty or Shuichi?
Yeah, I'm Shuichi. I'm here.
So do you see any capstaning much in the Japanese climber designs?
Stop. Stop. いや、I don't think so. But the Kanagawa University Egami Laboratory has the idea to, like I said, turn the roller axle to another way to control the whole climber. Like I said, she said. So they use the controllable axial system to tend the roller for another direction to control the attitude of whole climbers. So in usual, almost all climber has fixed axle, but there is some small idea for those things. Is that is that okay to be answered for the question?
I'm not sure I understood everything. So you're talking, is this the paper that has a climber where the configuration of rollers changes when they climb? Or
Like I say, the sun climber has the fixed roller axle and rotate like this way. But some climbers from Kanagawa University will control the axle angle, not only horizontal, vertical, same to the tether, but they use this kind of things to control the attitude or whole attitude of climber.
okay,
And some climbers will use this direction to climb up on the rope tether like this is the one idea for. So they think that it would be good for spin out technology for industrial usage. For example, the test of bridge wire check or investigation or something like that. That's
that sounds.
a small idea I know about the actual angle of tether climber.
Are there any papers that talk about that? I'd be very curious to know more.
Only in Japanese.
In Japanese, okay.
But so I'll try to find it.
Okay.
And how can I unveil or how can I send all of you? So. Yeah. So this kind of things. So almost all grammars study was take place under the control of laboratory of universities, and the student have to write the result paper for grammar that they build. Then it would be possible to find papers, but almost all papers are only in Japanese. But in these days, AI will translate in English would be easy. Then I will find.
Ono-san, is this one of the papers about that kind of drive? Because it has pictures like that.
This is just, I think that this is the paper for condition between the LoRa and tether.
It's the hybrid between a
And
capstan
then
and a pitch.
I think that the angle of each axle would not change, but the position of each axle would be move to control how the roller would contact against the tether, I think.
Yeah, so this paper I'm familiar with, and actually my presentation tomorrow, I'll point out why having all these
I see.
points is actually
Okay.
Right, but that might help.
okay.
Thank you.
Maybe I'll reach out to you offline to see if there's any papers in Japanese, like if there's figures and with Google Translate, I might still be able to make something out of them.
Deep L would be best way to translate the Japanese PDF in English. I see.
What is the best way?
Deep L.
Deep L free version would be up to 5 megabyte.
Okay.
They will accept up to 5 megabyte PDF file translation in
Okay.
free.
Okay. Thanks.
That's what I have on my phone.
Blaze, this is Jim here. I would think the drive would be more like serpentine rather than capstan, where the belt weaves in and out between the each of the rollers. You have contacts on two sides, so you have a larger contact area, but your disadvantages would be, instead of one large motor, you'd use several smaller motors, one for each of the wheels of your serpentine path and that. So there may not be too much of a trade-off whether you use the two-roller a pinch roller versus the serpentine route.
Yeah, I'm thinking you'd probably keep the same number of rollers, and in the reference design, they all have a motor attached to them, except that instead of putting them 2 by 2, you'd have them offset. What's the difference between serpentine and capstan? For me, those were the same.
Well, you're not old enough to look at reel-to-reel tape machines and that. And a capstan had a rubber wheel, which was like an idler wheel, and then it had a little pin on it that would squish it onto the rubber wheel, but the pin would drive the the tape. Or no, it may be the other way around, but you had a pin for pressure, and then you had just one drive wheel. So you had an idler wheel and a drive wheel, and the compression between the two.
Yep, I'm old enough. I see exactly what you're talking about.
Yeah.
You know, we had, when we had our ISEC conference at the Museum of Flight in Seattle, they also had, in conjunction with that, a junior high and high school climber competition. And in my memory, every one of those was a serpentine.
Mm-hmm.
Did they have good success?
Yeah, some of them actually went quite quickly up to it was only about 20 feet or maybe 30 to the top of the hull. And, but yeah, a lot of them went all the way up carrying payloads. And they were all weaved in and out of the rollers. So they didn't use a pinch at all. And probably because, it was just hanging there. There was no high tension on the tether.
Okay.
Another thing to keep in mind is to maybe attend one of these steam tractor threshing deals, and you'll see how they use belt drive for powering their equipment and that. These are all flat belts using rollers that have a convex surface on it, so that centers the belt over the wheel. If the belt drifts off center, it due to the convex nature, it will recenter the wheel, the tether in that. So maybe that can be looked at for, instead of using guides on the side to keep the tether onto the wheel, use the difference in the tension on the, across the width of the tether.
Yep, that's definitely something that I think would be interesting. Though I haven't quite wrapped my mind around whether the stretchiness of the ribbon would make that fail, compared to belt drives. But yeah, that's definitely a concept that that's interesting and that would not work with the pinch drive, but that might work with the capstan drive.
I had a question about like a lot of the modeling that was done during some of the presentations. What are some good tools to model the complex nature of a space elevator? Because there's oscillations and all kinds of things like that. What do you guys use?
Good question.
Tomorrow
We're in the process of developing those tools now. Jim already has
Yeah,
a well-tested
right.
tool. And
I will be showing my presentation towards the end of tomorrow, the Dimos to Mars elevator. And I'll give a very, very brief overview of the simulator I use and have developed over the last 20 years. So, you obtain the basis for it on an elevator design that, or not an elevator, but a tether system that Dr. David Lang produced for the space shuttle tether satellite tether power system back in the 80s. And the history of some of the code may go back into the 70s and so forth. So it's a very long-term development project to get it up to where it's at. And I'll give you an overview of that. We currently tried putting it up on the ISEC website, but it choked due to the current size is about 2 gigabytes. And when I add the Mars atmospheric thing or the revised Earth atmospheric, it'll double or triple in size again. So so we need an FTP site that can host the simulator for download. If you can suffer downloading a multi-gigabyte zip file or series of zip files. And then there should be a tutorial guide and so forth. But so for now, say coming soon, space elevator software at isec.org.
I'm working on a model too to do simulation and making some progress. I'll talk about that tomorrow as well. But we did a study on the simulations we wanted to do. This is the 2017 study on the ISEC webpage, if you want to go there and look at that one. That basically outlines a program that we want to follow for what we have to develop for all of this. So ideally, anybody who wants to develop a model, we hope would contribute it to us, and we can do comparisons and testing and things like that. But we briefly looked at things like using ANSYS and COMSOL and things like this. And my summer student and I ran in very quickly to the limitations of ANSYS for doing such large-scale problems. So you really have to examine the tools that you're going to use, and it looks like a lot of what we're going to have must be custom developed.
But TJ, it really depends upon what you're trying to model. I use a variety of different tools to build things, depending upon what I'm interested in. If you talk about hardcore math and integration and all that kind of stuff, I use Maxima, which is very open source, which is very similar to Mathematica. MATLAB Simulink is pretty good if you're looking at dynamic things. You want to take into account dynamic aspects of stuff. That's a pretty good tool. Excel works pretty good for certain things. You can build your own Visual Basic code if you need to, So it just depends what you want to do. There's lots of different software packages you can use to customize and do whatever you want to do.
I didn't know about Maxima. Thank you for that pointer.
It's actually Maxima is open source, and it was Steve Rolfe from when he went to MIT was exposed to Maximo, which is MIT code. He then kind of, I don't know if he bootlegged it or what he did, but he put a fancy GUI on the kernel and created Mathematica.
Huh.
And then,
Because Maxima's been around for a long time, hasn't it?
yeah, it was a Lisp code, and they tried marketing it when they saw him being successful marketing his product. They tried marketing it, but it was a bunch of MIT professors, and they don't know anything about marketing, so it kind of failed, and it went into open source. And the syntax is very, very similar to Mathematica. A lot of I've had trouble with some of the plotting routines because it's open source now. Some things that should plot, it just does, like some functions that just doesn't want to do them. But it's pretty good for open source code. It's just the documentation stinks.
Well, for you, Blaze, the Wolfram language, which is the open source version of Mathematica, plus Python interfaces gaining in popularity.
Okay. To answer the initial question, I think I'm kind of in the same camp as Stephen, where I tend to be coding up little models for whatever I happen to be doing. Like a general purpose simulator is valuable and has its uses, but usually I'm trying to analyze something that wouldn't be solvable properly by the general purpose one without using vast amounts of compute. And so I'm generally just coding up something in Python, whipping together a quick UI to allow myself to visualize it, and it's just typically like a few hours worth of work, and then I get the result that I'm looking for and move on to something else.
Right, I agree with that for getting a quick analysis of something. The simulation I did for the Dimos to Mars took a day and a half to complete, and that's at a very coarse resolution of the number of nodal points in the tether system. And that, so saving time. If you don't need to take all that time if you have an alternate way to get the piece of information you're looking for. So.
Did Jim just drop out?
No, I'm here.
Oh, okay.
I
Just
think I
everybody went
finished.
quiet. Yeah. Okay.
I put everyone to sleep.
Hey, it's Saturday night. We're having fun.
Yeah.
Well, for some of us, it's Saturday night.
One other question I was thinking of, do you guys know of companies that are already starting to do the engineering work on these, now that we have the materials, I'd be curious to see their approaches.
On the materials? Yeah, several of them are. There's LG. There's a graphene company in Oak Ridge. What's their name? It's not National Graphene, but something like that. They're working on it.
TJ, you also have to recognize that because of the economic possibilities, a lot of them are keeping it close to the vest. So
Understood.
So you're going to see a lot of people locking down, saying it's a trade secret or intellectual property or something. So sometimes they'll do business to business kind of dialogues, but Joe Public, they're not going to divulge.
What are they?
That's fair.
Is it the processes or is it the final performance they have? Because you'd think that once they have something performant, they'd want to sell it to whoever wants to buy it.
I think it's all the above, because I know that with a lot of the technology I developed, you want to control the information because people can misuse it and give you a black eye. As you're developing something, you might find that if you're focusing on one attribute, you're making others suffer while you're focusing on one attribute. Then you go back and you work on the other ones and beef them up. But if the word gets out, you stink in one attribute, you're going to lose a lot of people's interest. The well is already poisoned, so you got to be very careful about controlling information as you develop certain things.
Right, and there'll be a lot of trade secret type of stuff that will be going on until they figure out how to do that delamination off of the substrate that you put it on. It reminds me of one of my customers in my software company stuff was Appleton Papers. They manufacture paper, and they had one machine would always put out better paper than all the other machines, and they were trying to figure out why it was, so they had to put a spy in their own plant to observe what the guys who were running the machine were doing, and they noticed that one of the guys was urinating into the vat. And it turned out that the urea acid in the urine made better quality paper, so they learned how to put that in. But that's a deal that some key magic sauce, so to speak, that you put in your manufacturing process will make you better than everyone else, and they're going to keep that a secret until they can milk that as far as they can. Then they'll try to patent it and take that for another 17 years.
So did that guy get rewarded or fired?
He got kind of rewarded and kind of fired, So, but that was kind of neat. But that's an example of a manufacturing process that nobody thought of, but it improved the quality of the product that came out. And I suspect that will happen in the production of these graphene systems.
One of the things that I think we're up against in getting large-scale graphene production is that the current graphene companies are doing very well producing powders and
Right.
little crystals of graphene rather than sheets of it. And they don't see any motivation to depart from this. And I think we need to motivate a market that says you really need these big pieces.
Mm-hmm.
But yeah, there's some kilometer
structures.
scale production going on, and that's taking it off of copper substrate, I think.
There's one thing we have to consider as far as like an industry or whatever it might be. There was a big difference between, in the early days of electronics, there was Silicon Valley, and then there was the 128 loop.
Mm-hmm.
The 128 loop kind of collapsed because it was hyper competitive, everything was a secret, that kind of thing. Silicon Valley flourished because it was very open, and they were more about just developing whatever it was that they wanted to get developed. And they knew eventually somebody would win, and somehow they'd all pile on. So it depends upon, are we going to create a environment where it's highly competitive, or is it more collaborative? Will it work in this industry like it did in Silicon Valley? And that's what we have to really contemplate, is that can we loosen up the trade secret hoopla and a bunch of other things and be more collaborative in nature? And I think that's what ISEC is attempting to do. But I don't think the industry as a whole will totally embrace that, although it would be in its interest.
Well, I somewhat disagree with that scenario. I think Silicon Valley was more of a case of jumping ship. When you leave one company to form your other company and so forth, and they didn't have non-compete clauses and all that other business back then, and as much as what they're doing now. So, Fairchild broke off from the Shotley and Bardeen and the other guy, and then Intel and the rest of them were fractured off of them and so forth. So I think it was more of mutation type of deal that drove the technology than it was, openness of, trade secrets and that.
Well, it depends upon what you read.
Yeah.
I'm curious, someone mentioned the peeling, and like there was a lot of talk about it in the video, but I didn't quite get the significance of the little video snippets he was showing with the peel. Did someone else understand that and could maybe explain?
What he was saying is that they currently need a, it's not a catalyst, but it's similar to catalyst. It's a condense surface to make the atoms join up into their hexagonal pattern. And one of the surfaces is copper, and he listed a few other metallic surfaces that aid in it condensing into the shape. But the problem you have then is, how do you delaminate the graphene from the subsurface that it's on? And currently the first attempts were to dissolve the copper out and leave the the graphene there, and that was a very slow process. And so now they're investigating the best ways to separate the graphene from the substrate that they form it on. And one of the deals is the using molten copper, which has apparently a colder melt point than the condensation point of the graphene. And so how you separate that, you got to somehow pick it up off the molten copper before you can put it on your spool in that. And they were showing how they might be able to do it with an argon burst of gas, that would separate the layer with a gas jet, and that, and then you would spool up the graphene on the once it's free from the surface there. And presumably you'd circle the molten copper around, kind of like they do plate glass, how they do put the glass on top of the molten tin in that, and when they manufacture plate glass and that.
Okay, but there were several videos where he was showing like basically peeling tape off a surface, and I didn't really understand the difference between those.
Well, ignore the fact that it's tape, and then imagine instead of tape that this is the graphene, and that the board was a board with white paint on it that he was peeling it off. And imagine the board is your copper, either the solid copper or molten copper, and you have to somehow pick the graphene up and separate it from the
But what was the difference between the videos? That's the part I didn't get.
Well, one of them, he was trying to blow it with a jet to, instead of a mechanical force of peeling it, and the other, he was using an air jet to try to separate the, which wasn't too successful. But that was the other
Yeah, if
example.
if it's a liquid substrate, it may not be all that hard, and you could do it with an air jet, or argon rather.
Right, assuming the surface tension isn't stronger than the thing, and you would lift up the copper with the sheet of graphene. Yeah.
There was a whole slide basically on speeding up the peeling process. If you look back through the slides, and I think the peeling speed is just the limitation for the process, right? As far as I understood it. So
yeah,
peeling is a very tricky matter. If you have looked into peeling, it's not a simple matter to assess how that works. So
right, but someone will figure it out, and then you do it more in parallel, and now your one plant can do, just like they do fabric and very large, knitting machines and so forth.
It's a complex optimization problem.
Right.
But Blaze, there's other companies that are looking at various substrates besides the coppers. And it always gets back down to is how do you separate the graphene from the substrates?
Right.
And that's what his whole discussion was about, is trying to figure out, well, what's the best way to separate a sheet of graphene from a substrate material?
Now, it's unfortunate he wasn't available for questions. I was going to ask, when they do the N layer, the 4 or 5 layer graphing on top of the substrate, does the next layer form between the substrate and the prior one, prior layer, or does it form on top of the graphene layer?
Comes very
does
There
it-
are a number of different ways of doing that. A lot of people are right now forming 10 layers at a time. It depends on the gas flow.
But do the layers form on top of each other layer, or do the layers form between the substrate and the bottom layer?
Again, it depends on how you do it. Some of it is actually diffuses up through the molten substrate. So a lot of this carbon, you send in you send in methane into the bath, and that dissociates the hydrogen, and the carbon floats up toward the surface through the metal, and it connects to the underside of the existing layer.
Okay.
I haven't kept track of the solid substrates to determine if they're doing multi-layer or not. But I would assume that they'd have to come from the top on that one.
Okay, if it's coming from the top, then it condenses on top of graphene, which
Yeah.
means you could conceptually just pass a graphene ribbon through a furnace and then have it condense on top and possibly on the bottom at the same time, and add 2 layers each time you pass it through your oven.
Yep.
Once you have the first layer built, yeah.
Yeah.
Right.
So that could give you your process. You run it through 100 layers of stuff, like putting extra layers of paint on it.
Yep, that sounds good. Actually, go ahead and send an email to Rod. He's pretty good at answering.
Yeah.
Is his
Well, I don't have his email.
Oh, all right.
Kind of send it to the group, the ISEC group or something like that.
Yeah,
Somebody
I'll do
put it
that.
in the
In the
chat.
chat.
It is in
The
the
chat
chat,
window?
right?
It's in the chat already. Okay.
Okay.
Yep.
All right, I'll open that up.
Lauren put it up there.
Is his talk going to be on the website?
That's a good question. Apparently it's quite large now. So what I'll do is ask him to extract his slides only, and then maybe get a few stills from the movies so that it won't be so big. So I will ask him to put it to submit it to the website.
What about the Zoom recording? Is that going to be available?
Yes.
Excellent.
It'll be on my Zoom cloud account, and I'll send you a share to it, just like we do for the power meetings.
Cool.
And then if someone wants to edit it, we can download it. And I think David Brand Erickson wanted to chop it up into individual speakers.
Will it be okay if I post my talk to my YouTube page?
That's what I
Yeah,
do.
no reason not to.
Problem? Cool.
Okay, well, we're a little bit past our ending time, but it looks like we're dwindling a little bit. But we will start up again tomorrow at 9 a.m. Chicago time and 11 p.m. Seoul and Tokyo time and 3 p.m. London time. And Adrian's going to start talking, so we're going to hear more about materials manufacturing.
Tomorrow's session is a little bit longer than tonight's was.
A little bit, yeah.
Thank you, Dennis.
Well, thank
Larry.
you all.